Hello, good evening. Am I audible?
Yes, sir. Good evening.
Okay, good. We'll wait for a few more minutes. People are still joining, and then we'll begin the session. Um, just to summarize, just to remind that this is the sixth session for NPTEL Physics, and my name is Amit. I'm taking the electronics section. We were doing op amps. The previous two sessions were related to op amps. This is the final session that is related to op amps. Um, have you seen the updated calendar for physics? Has it been updated? If you know.
Yes, sir. It's been updated.
Okay, so for the next three sessions, not today. So next week, next Sunday, and then the two Sundays after that, we'll be doing logic gates and primarily logic gates, Boolean algebra, and after that we'll be doing some. There are some JK flip flop questions related to JK flip flops and counters and analog to digital converter, digital to analog converter. So that will be our next 3 weeks from not this week. The coming 3 weeks will be that, and the final 3 weeks will be on diodes, BJTs, and FETs. So that will complete every topic in electronics, every subtopic in electronics. We started with simple KVL and KCL, and then for the next 2 weeks we did some semiconductors, and then 3 weeks of op amps, then 3 weeks of digital electronics, and final 3 weeks of diode, BJT, and FET. So that's the idea. You're welcome to send me any doubts or ask in class or concepts. If you have any doubts, you are more than welcome. We'll wait for a couple of minutes, and then we'll start. So net exam is completed, right? That was yesterday, if I'm not wrong. Yesterday or day before, right?
16, yes, day
Okay.
before.
Okay. ठीक है. So did you people attempt that? Wrote that exam? Any one of you?
Yes, sir. Yes, sir.
So how was the overall, and particularly how was the electronics portion?
Sir, my electronics is very weak, so I does not attempt too many questions from
Okay,
electronics.
okay, it's fine. Hopefully, this will help you. These sessions that we are conducting. Anyone else about
I
electron?
searched for open question but couldn't find. I find a question on feedback, but I was not able to attempt. I tried, but
Okay,
sir didn't.
okay. What was the question on? Op amps, you said?
No, I said feedback. I was searching for open questions because in the
Okay.
previous class I have learned about open.
So feedback related to what? Is it control system? I am not.
Amplifier.
Okay,
It was given that the amplifier output is 40, the gain is 40 dB
okay,
decibel, and the 140 of the output is uh, feedback to the input. So, what will be the change in the output? It is something like this question.
okay, okay. ठीक है. I'll touch upon this, that what is the gain? How do we measure the gain? So will touch upon that. Okay, I think we should start now. We have waited for 5 minutes. If other people join, um, I'll just summarize for them once again. Okay, once again, welcome to week 6 of Gate NPTEL sessions. I'm going to start sharing my screen. Is it visible? Hello.
Yes, sir.
Okay. Okay. So this is week 6 of GATE NPTEL solutions hosted by NPTEL. My name is Amit. We were doing the OPAM section. So here is just a very quick summary of what we have discussed till date. An operational amplifier does some operations like comparison, integration, differentiation, addition. We have seen questions related to each of these. In fact, each of these questions has been asked in GATE exam. Why is it amplifier? Because it amplifies the input voltage, and it's subclass of differential amplifier. This means this is your typical differential amplifier with a differential gain AD and a common mode gain AC. So if we put this condition that AD is greater than AC and it has a low output impedance and high input impedance, what we get is a operational amplifier, and this is a typical symbol of operational amplifier where we have two inputs. This input is called non-inverting input, this input is called inverting input, and from here we get the output, and these are the saturation voltages. So saturation voltage, so output of an amplifier cannot go above this saturation voltage Vs plus, and it cannot go below Vs minus, the negative side of the saturation voltage. Right, so this is just a zoomed in picture of the operational amplifier. So we have the two inputs, as I told, non-inverting and inverting. The saturation voltage Vs plus and Vn minus, the V out. This is the model of an operational amplifier, and these are some typical some parameters that we encounter while we discuss op-amps. And I summarized what is the ideal value that we expect and what is the real world value that we typically get. So we have seen open loop gain, we have talked about output voltage, we will talk a bit about input and output impedance in this class. This we have not yet encountered. Bandwidth we'll see today, slew rate we have not yet encountered, and this again we usually don't get, but we'll see something similar to this, and hopefully it will get more clear. So this is the summary of this is in fact the only formula that we have to remember as far as operational amplifier is concerned. So as I told you, non-inverting input, inverting input, and AOL is the open loop gain. So and what we have is KVL and KCL, and that's it. That's all we need to remember. Right, now we'll quickly start with the questions for today. So okay, so this is a question. This has been taken from 2013 paper, slightly older, but it serves our purpose. So it says a low pass filter is formed by a resistance R and a capacitance C. Okay, so at cutoff, the angular frequency omega equal to 1 by RC, the voltage gain and phase of output voltage related to input voltage is. Okay, so first we must understand what a low pass filter is. So a low pass filter, excuse me, some people are trying to join, excuse me for a minute. All right, so a low pass filter, as the name suggests, it will allow low frequencies to pass through. Okay, what this means? So it means something like this. This is frequency in hertz, and this is the gain. We typically measure gain in dB. So the formula for gain is 20 log V output divided by V input. So this is gain in dB. So we have seen the formula for V out upon V in. This we always find in our questions. We simply take a log of it and multiply it by 20. We get the value in we get the value in dB. So low pass filter looks something like this. This means it will give high gain up till a certain point, and then the gain will start to reduce. This is a low pass filter. I'll change the pen. So this is a low pass. Right. While we are talking about filters, let's talk about one more filter, which is high pass. So again, this is frequency in hertz. This is gain in dB. So that one looks something like this. This means at lower frequencies, you see, this is the lower frequency. In lower frequency, you will get very less gain. This means V out will be very low. So V out is low, however at a certain cutoff frequency, this is the cutoff frequency, above this we'll get high gain. So this is a high pass filter. So this is a low pass filter, as it shows that only the gain is high only at low frequencies. This means V out will be high only at low frequencies, right? And it will be low at high frequency. This is a low pass filter. The converse is true for a high pass filter. So in this question, let me change my pen again. So in this question, what we are told, a low pass filter is formed by a resistance R and a capacitance C. So first we must understand how the circuit, this is a typical circuit, that's how it looks like. So I'm going to draw this circuit there. Okay, so this is V in, this is R, this is C, this is grounded, and this is where we take the output. That's simply the circuit for a low pass filter. This is a low pass filter. Okay, now what was given to us in the question, we need to find out the voltage gain and phase of output voltage. Okay, so we need to find out, excuse me, we need to find out gain. This means V out upon V in, its magnitude and phase. Okay, so we'll simply first derive the expression for V out over V in. How do we do that? Very simple, just apply KVL in this loop. Okay, so let's assume a current I is flowing in this direction. I'll write my KVL like this. So V in minus I times R minus, okay, now we know the reactance of a capacitor is 1 upon j omega c, or rather I should say, you can say it ZC. ZC is 1 upon j omega c. So we can simply write minus IR minus I into 1 upon j omega c equal to 0. I have just written KVL in this loop. Okay, let's solve it. So value of I will come out to be V in by R plus 1 upon j omega c. Very good. Now V out I can write as, how do I write V out? I just apply Ohm's law across this capacitor. So that will be V equal to I, because I is the current flowing through this capacitor, times C, times R. The impedance of this capacitor is 1 upon j omega c. So V out will come out to be V in divided by R plus 1 upon j omega c, that's the value of I, multiplied by 1 upon j omega c. Now simplifying it further, so what we get is, so I'll apply j omega c in the denominator, so I'll get j omega c times R plus j omega c times 1 upon j omega c. So this will give me V in upon 1 plus j omega RC, right? So but we needed to find the gain. So gain is V out upon V in. So this will come out to be 1 plus j omega RC. I'll write it here again. Okay, so using a different pen I'm writing it. So I can say V out over V in, this is the gain, voltage gain, is equal to 1 upon 1 plus j omega RC. Okay, now we were required to find out the magnitude and the phase of this number. So this is what we are required to find, and omega was given as 1 by RC. We were required to find out the gain, the magnitude of gain and the phase of gain at a frequency equal to 1 by RC. This is called actually the cutoff frequency. Why it's called cutoff? Because at above this, below this, so it is a low pass filter. So as I told you, the graphs look something like this. So this frequency is nothing but 1 is denoted by omega c, which is in this case is 1 upon RC. This is frequency and this is gain. It's called cutoff because below this the amplifier is, the circuit is not conducting, it's giving very low gain. However, above this it will give high gain. So we simply put the value of omega is given in the question is 1 upon RC. So I'll get 1 upon J 1 upon RC into RC. This gets cancelled. So I get 1 upon 1 plus J. Okay. Now this is simply, so we have found the expression for gain now. Now we were required to find the magnitude. I'll simply just multiply numerator and denominator by 1 minus J. I am rationalizing it. So this will come out to be 1 minus J over 2. Okay. Now what's the magnitude? So magnitude we can simply find out as, so magnitude of gain is under root of 1 by 2 square plus minus 1 by 2 square. This is 1 by 2 into root 2. So this will come out to be root 2 is 1.414 divided by 2 is 0.707. This is the magnitude, and phase of gain is given by the imaginary part divided by the real part. So it will be tan inverse minus 1 by 2 divided by 1 by 2 tan inverse of minus 1, which is minus 45 degrees. Okay, so we got the expression, we got the answers as 0.707 and minus 45. 0.70. Okay, so this is the answer. 0.707 has been rounded off to 0.71 and the angle we find out is minus 45. This is a very simple question. Again, I'll summarize what we have talked about just now for this question. So a low pass filter question was said that we have to, a low pass filter circuit is to be formed with a resistance R and a capacitance C. So this is how a low pass filter circuit looks like. We take output across the capacitance and input is applied through the resistor. Okay, and the cutoff frequency was given as 1 by RC. Cutoff frequency was given at 1 by RC. We were required to find the gain and phase of the voltage gain R. This is what we are required to find out. So we were required to find out the magnitude of gain and the phase of the gain. So we simply applied a KVL in this loop. We found out the expression for V out upon V in using some very simple algebra. This was the expression, and then we simply put equal to omega C, which was given as 1 by RC. We put it, this was the expression that we got, 1 upon 1 plus J. I rationalized it and we found the gain magnitude to be 0.707 and the phase to be minus 45 degrees. This is what a low pass filter looks like. Excuse me for a minute. All right, now we'll use this concept in our next question. Now see, the gain here that we got was 0.707. This is a very bad amplifier. We are not getting any gain. So let's say you apply 1 volt of input. What you will get? You will get only 0.71 volts of output. This is not even amplifying. Hence, in order to use a low pass filter, you also have to amplify the voltage, and hence what we do is we use an operational amplifier. So you see, this is your low pass filter. Remember that. This is nothing but your low pass filter. And on the right half, in the right half, this is an amplifier. This is an amplifier. So when we cascade these two circuits, when we use them back to back in series, what we get? We will get a low pass filter with amplified output voltage. Remember, a low pass filter will not necessarily amplify the voltage. However, when we use it in series with an operational amplifier, in cascading with an operational amplifier, you can get a low pass filter with amplified voltage, and we'll see how we do that. Right. Again, this question is from 2013, so both the questions are from 2013. So what we see here is this is, so input is being provided. Okay, so again, every op-amp question we do three things. Is the op-amp ideal? So the question does not say anything. Assume ideal. Second, is there a feedback? Is there a feedback? So V out is connected to plus terminal. Yes, there is a feedback. Yes. What kind of feedback? Positive feedback. Third, the input is being provided at inverting terminal, sorry. So this is an inverting circuit. This means output and input will be out of phase. Simple. So let's try to solve this problem, and we'll use the concept which we have done in the previous question. Again, very simple, nothing fancy will happen. So I'll redraw this circuit. I'm redrawing the circuit. Okay. Right. So what we are required to find? We find the circuit. For this circuit, the frequency above which gain will decrease by 20 dB per decade. So this is the definition. This thing is the definition of cutoff frequency. I told you, for a low pass filter which looks like something like this, so this is the frequency above which the gain will start to drop, and this is called the cutoff frequency. This we are required to find this, and also we need to find the closed loop gain at a given frequency. We'll do that, that's not a problem. So closed loop gain is nothing but V out over V in at omega equal to 1.2 kilohertz. This is what we require to find. Fine, we'll do this. Okay, so this is the circuit. So first we need, let's find, first of all, to simplify the things, let's just simply find out what is the voltage gain first. Let's simply find out what is V out by V in. Okay, since we know this is an ideal amplifier, so no current will flow here. So I equal to 0, no current will flow here, I equal to 0, and no current will flow here, I equal to 0. Again, ideal amplifier, this means virtual short. And as I always do, I assume this node has voltage Vx. Right, so let's apply. Okay, let's try to find the value of this Vx. Okay, remember that we can simply write this as 1 upon j omega c, where c is 1000 picofarad. I'm calling this resistance as R1, this as R2, this as R3. We'll see, just for the sake of writing, because I'm deriving a general formula which can be used anywhere. Right, so let's just find out the value of Vx first. Okay, so I'll simply, let's say current I is flowing here. So applying KVL in this loop, I can write V in minus I R1 minus I into 1 upon j omega c equal to 0. So I get value of I as V in R1 plus 1 upon j omega c. Now the value of, in order to find the value of Vx, we apply Ohm's law across this capacitor. What is Ohm's law? Ohm's law says voltage across an impedance, in this case is a capacitor, is equal to current flowing through it. So I, current flowing here is I, times the impedance. What is the impedance? 1 upon j omega c. So I write the value of V in R1 plus 1 upon j omega c into 1 upon j omega c. I'll get the expression V in upon 1 plus j omega R1c, which is we derived for, this is nothing but low pass filter. So here we have taken the output from here. I just derived it again just for the sake of completion. All right, but we need to find the value of, we need v out by v in, not vx by v in. So how do we find that? Now we apply, okay, correct. So no current is flowing through here, I is equal to 0 because no current is going here. Let's assume a current I1 is flowing here. So whatever current is flowing here has to flow through here because no current can go here. Okay, so and this voltage is nothing but Vx. Remember, this is virtual short, so the voltage Vx is the Vx same here, and this is a wire. This is a wire, so the voltage here is also Vx. So I'll write the current Ohm's law across this resistor. I'll write V naught minus Vx divided by R2. This is the current I1. I'll also write Ohm's law across this resistor. So I can write Vx, I should say like this, sorry. Ohm's law across this resistor will be V naught minus Vx equal to I1, the current flowing through this resistor, times R2. This will give me I1 equal to V naught minus Vx upon R2. Now I apply Ohm's law across this resistor R3. So the voltage across this resistor is Vx. Note that this voltage is Vx because of virtual short. Vx minus 0, this is 0 here, equal to current flowing through this resistor, which is I1, times R3. I'll get the value of I1 as Vx upon R3. So these two values have to be equal. Note that. So I can simply say V naught minus Vx upon R2 equal to Vx upon R3. This will give me V naught equal to Vx 1 by R2 plus 1 by R3. Now we know the value of Vx, so let's put this value of Vx here. So I get V naught equal to V in divided by 1 plus j omega R1c times 1 by R2 plus 1 by R3. Right. So I'll write this expression on the next slide. So we got V naught equal to V in upon 1 plus j omega R1c multiplied by 1 by R2 plus 1 by R3. Right. So gain is nothing but V out upon V in, which will come out to be 1 by R2 plus 1 by R3 divided by, right, yeah, correct, right? So Vx goes here, yeah, very good. Now what were we required to find? We will find the frequency at which gain will decrease by 20 dB per decade. So this is the expression for gain. So how to find the frequency at which it decreases by 20 dB per decade? You simply say whatever the coefficient of j equal to 1. So question 1, how to find cutoff frequency? Cutoff frequency is given by omega c. We do it by putting this whole expression omega c R1c equal to 1. This is the definition of cutoff frequency. So coefficient of j has to be 1. So I will simply say omega c equal to 1 upon R1c. Now the value of R1 was 10k times 1000 picofarad. So this will come out to be nano. So this is 10 to the 9 divided by 1 by 10 to the power 4. So this will come out to be 10 to the power 5 radians. But I think the options are in hertz. Yeah, the options are in hertz. So we'll simply need to convert it into, so the frequency can be written as 2 pi omega c. This implies, sorry, omega c by 2 pi. So f will come out to be 10 to the power 5 upon 2 pi hertz. So 10 to the power will be something, this will be 10 to the power 5 upon 6.28 hertz. This will come out to be around 15 or 16 or something. 15 or 16 kilohertz. Is there an option like that, 15 or 16 kilohertz? Yeah, there is. Okay, good. This is the answer, right? So what we did here was that for this given circuit we found out what is the gain. This is what we derived here. So this was the expression for a low pass filter. Here I simply wrote just Ohm's law, and we found out this expression for gain. This is the gain expression. What is the cutoff frequency? Cutoff frequency is when we are in the form of 1 upon j omega RC. So we simply put the coefficient of j equal to unity. Remember, the form has to be like this, 1 plus j omega RC. So omega c, so this is called the cutoff frequency, omega c. So omega c equal to 1 upon r1c. I simply put the values, converted from radian to hertz. So we got the answer, 15 point something kilohertz. Now the second part was we need to find the gain at f equal to 1.2 kilohertz. Let's try to find out that, right? So gain is, so what is the gain? This is the value of gain. So this is gain equal to 1 by r2 plus 1 by r3 divided by 1 plus j. The value of omega is given as 1.2 kilohertz. So this implies omega will be 2 pi f. So this will be 2 pi times 1.2 kilohertz. Let's put it here. So 2 into pi into 1.2 kilohertz times r1c. The value of r1c we calculated as this. So 1 upon 10 to the power 5. Okay. The value of r2 and r3 was given to us, 1k and 2k. So I'll write 1 plus 1 by 2 divided by 1 plus j. So this will come out to be 2 pi into 1.2. This is k, so that's 10 to the power 3 upon 100. 3 by 2. Numerator is 3 by 2. 1 plus j. Let me just get my calculator. I'll try to find out this exact value. 2 times pi times 1.2 divided by 100. So that is 0.075 into 0.075, right? So as I told you, we were required to find the gain in dB. Okay, so how do we do that? We simply say, wait, is it in dB? No, not in dB, sorry. So we need to just simply take the magnitude of this thing. So this will be, so the magnitude of this will be, so gain magnitude, this will be magnitude of 3 by 2 divided by magnitude of 1 plus j 0.075. So magnitude of 3 by 2 is 3 by 2. This will be 1. Why this will be 1? Because this quantity is very small. Even if you use the calculator, since this is less than 1/10, so 1 plus, even this were 0.1, we would have neglected it, because see, the square of it will come out to be 0.0005. Okay, and if you add 1 to that, that's a negligible number, so it will not impact it too much. Okay, or maybe 0.005, whatever, but we can neglect it. So the answer would be 3 by 2. So the answer would be 3 by 2 is 1.5. Now I told you, so this is cutoff frequency we found out as 15.9 kilohertz. This is the cutoff frequency find out. I told you below it we'll get high gain. So we are getting a high gain of 1.5. This is 1.5. Remember that in previous question, what was the gain? Gain was less than 1. It was only 0.7. We found out this 0.7. However, when we have used an amplifier, we are able to increase gain to 1.5, and we can increase it further, because gain is determined only by R2 and R3. Note that. Gain is determined only by R2 and R3. So if I use lower values of R2 and R3, we'll get a higher gain. It's very straightforward. So yeah, so that's what we did in this problem. And now let's move forward. So remember that when we were talking about ideal op-amp, their ideal op-amp, we assume that noise is 0. We never talk about it. We assume that this op-amp is ideal and it will suppress any noise. So let's say you are providing an input signal like this. You want to provide an input signal like this. So this is your input signal with time. However, due to some noise, input signal in real life is something like this. So what you see superimposed on this input signal, the variation from, this is ideal input, sorry, this is non-ideal input, non-ideal input, this is ideal input, this is time. So we assume that the operational amplifier that we have, V out, V plus, V minus, will be able to suppress any noise that we provide. This is what an ideal operational amplifier does. However, it's not ideal. So you can see that instead of being infinite, it is minus 50 dB. This is called ripple rejection. Ripple rejection is nothing but how much noise in input can be suppressed by output. So the formula for ripple rejection is, this is very similar to your common mode rejection. So ripple rejection can be given as 20 log V out by V in. Okay, so we should say V out ripple divided by V in ripple. Okay, so ripple rejection, this is in dB obviously, because we are using the form 20 log. So ripple rejection is minus 50. So I'll simply say minus 50 equal to 20 log of V out ripple. We need to find out that. So V out ripple, we need to find this out, divided by V in ripple. V in ripple is given as 1 millivolts. So I'll simply just cross multiply this. So I'll get log V out ripple divided by 1 millivolts equal to minus 2.5. Okay, so this will come out to be V out ripple over 1 millivolts is 10 to the power minus 2.5. Let me use my calculator. What's this value? 10 to the power minus 2.5. Okay, so this is 3.16 into 10 to the power minus 3. This is 3.16 into 10 to the power minus 3. Now simply multiply this here. So I get V out ripple equal to 3.16 into 10 to the power minus 3 millivolts, which is nothing but 3.16 microvolts. So okay, so we are required to find the answer in microvolts. So the answer is 3.16 microvolts. Again, a very simple question based on a very simple formula, just like a CMRR. Remember CMRR, common mode rejection ratio, which was given as 20 log AD over AC, or was it inverse? I always forget this. I think it's AC over AD. Yeah. So similarly, what does ripple rejection mean? Ripple rejection means how much in the noise in input can be suppressed when it comes to output. Note that the noise in input was 1 millivolts. The noise in output was 3.16 microvolts. This is a very good operational amplifier. Why? Because it has reduced the noise from the units of, from the order of microvolt, from the order of millivolts, sorry, to the order of microvolts. That's a 3 orders of reduction. 3 orders of reduction. This is very good amplifier. Very good amplifier. Very good amplifier. Why? Because it's suppressing the noise. So even if there is a noise coming input due to various reasons, like somebody stepping on a wire, walking on it, or there is some environmental noises, any kind of disturbance is suppressed to a very good extent, to 10 to 3 orders. That's a very, very good operational amplifier which is able to reduce the ripple to 3 orders. It's a very good operational amplifier. Right. So this is the last question that we have for op-amps. This is the very last question. So I wanted to end with a theory question so that I can summarize everything that we have talked about till now. So what we are given is that an op-amp based negative feedback non-inverting amplifier. Okay, so we have a negative feedback. So let me draw this. This is minus plus. So let's say and let's say we are providing input from here, output. Why? Because it was saying non-inverting amplifier, so we have to provide input to the non-inverting terminal, and it's a negative feedback, so I've connected the output voltage to the negative terminal using some feedback resistor RF, and in order to complete the circuit we will have a resistor here as R1. I'm not using any capacitors because the workflow remains the same. It's just that you can write the impedance as 1 upon j omega c, and everything else remains the same. So our understanding does not change, the basics remain the same. So this is the circuit that we are given. Now, which of the following statements are true? Closed loop gain is less than open loop gain, which is true. Remember that. So always the formula which comes out to be here, if you recall, it was always of the form of 1 plus RF by R1 or something like this. This we had derived in earlier, I think previous class also. So always the nature of the gain is something like this, 1 plus R. However, the open loop gain, I told you, is order of 10 to the power 5. This we also saw in this slide, in the very first slide which we talked about, right here. Yeah, so I told you the real value open loop gain is typically 10 to the power 5, right? While we apply when we apply a feedback, we suffer in terms of gain, so gain goes down. So this is correct. So on applying the feedback, gain usually goes down, so this option is correct. Now what happens to the bandwidth? Okay, so there is a concept called gain bandwidth product. For a given circuit, gain bandwidth product has to be constant. So I can simply say, let's say gain for closed loop multiplied by bandwidth of closed loop should be equal to gain of open loop multiplied by bandwidth of open loop. Now, so I can say bandwidth of closed loop divided by bandwidth of open loop should be equal to gain of open loop divided by gain of closed loop. We know that this is greater than 1, this quantity, so this implies bandwidth of closed loop should be greater than bandwidth of open loop. What's the bandwidth? Bandwidth is the range of frequency in which signal is high. So we saw that low pass filter something looks like this, right? So this is a low pass filter, so this is the frequency for a low pass filter, bandwidth, sorry, this is the bandwidth, because it is conducting in this stage. For a high pass filter, which looks something like this, in which the bandwidth is this. So this is for low pass filter, and this is for high pass filter, right? So we talked about these two things, sorry. So what we saw was that closed loop bandwidth is higher than open loop bandwidth. So this is wrong, the sign is wrong, so this option is incorrect. So this option is incorrect, right? Next, closed loop input impedance and open loop input impedance. Okay, so how do we find the input impedance? As I told you, the signal, the circuit looks something like this, R1, V out, this is RF, and we provide an input signal from here, right? I've always told you that in an ideal amplifier there is this Rin is here, and this is assumed to be infinity, and there is an R output, R out here also, and there is a, so I'm talking about this circuit, we talked about this circuit. So you see, this is the Rin. We usually, in ideal case, we assume it to be infinity, however real value is in some mega ohms. Similarly, output voltage, ideal value is 0, reality it's in some ohms or some milliohms. So this is a circuit that I'm talking about here. All right, so yeah, so this is G times V plus minus V minus, this is grounded. So this is the actual circuit which how it looks like, right? So now it's saying that what is the input impedance for this circuit? What is the input impedance that we see, and also what is the output impedance that we see for this circuit, right? So again, using some KVL, KCL and some algebra, so what we can find out is that Rn for closed loop, remember that Rn for closed loop comes out to be 1 plus AOL over ACL times Rn of open loop. So Rn of closed loop is 1 plus AOL. AOL is nothing but open loop gain. ACL is nothing but closed loop gain times Rn. Now, if I want to see the ratio of Rn closed loop divided by Rn open loop, this is 1 plus AOL upon ACL. And we know that open loop gain is higher than ACL. So this quantity would be greater than 1. Thus, Rn closed loop should be greater than Rn open loop. So closed loop input impedance should be higher than open loop input impedance. Similarly, just like this, there is again an expression for R out of closed loop is equal to 1 upon AOL upon ACL times R out of open loop. Again, you can simply just say R out of closed loop divided by R output of open loop. This is equal to 1 plus AOL upon ACL, and since this quantity is always greater than 1, so this will also always going to be less than 1, because new denominator will always be greater than 2 in this case, at least greater than 2. So this will also always be less than 1, and hence R out of CL will be less than R out of open loop. So these two are the expressions. So similarly, we can say that this is the answer for us here. Okay, yeah, so this summarizes this open loop. Usually input impedances and output impedances, for all practical purposes, usually these are not asked. So this is a very I should say theory based question. So there are derivations involved, there are quite a lot of formula involved. That's why these are usually not asked in exams, but for the sake of completion, you must know that we derived these formula for gain and everything. Similarly, using KVL, the formula for input impedance and output impedances can be derived. It's not something that's very difficult to do, and we'll try to see that. I think this input impedance and output impedance usually comes up, I don't know, maybe in some bachelor classes you might have seen that for like MOSFETs or BJTs, if there is small signal models involved. But for operation amplifiers, it's very straightforward. You just have to remember these two. That's it. It's the ratio that matters, and that's all we need to remember. So yeah, so that's it from me. Today's session was short because I had exhausted the questions earlier also. So if you have do you have any doubts regarding previous class or in this class, low pass, high pass filter, anything that you need to ask me? If you need me to repeat some question. Anything?
Sir, can you explain again CMRR?
CMRR. Okay, I'll do that. Hold on. So usually the gain of of an amplifier is given as AD times difference in inputs plus AC times. So I'll have to show you that more clear. Yeah, you see this expression here? You're able to see my screen,
Yes.
right? So this is the expression that we have for V out. This is a typical amplifier expression, differential amplifier expression. So we have two inputs, V in plus and V in minus, and we are getting the output across these two terminals, which is given as V out. So this AD is called differential gain. This is called, AC is called common mode gain. So the name is explanatory actually. Differential. Why differential gain? Because the inputs are being, we are taking as difference of inputs, so hence differential gain. Why common mode gain? Because we are taking the average of inputs. So this is whatever is the common is being taken, and whatever is different between these two inputs, which will be multiplied by AD. So this is the general expression. For op-amp, I told you, for op-amp we get AD greater than AC. If this condition is satisfied, for a good op-amp, this condition is satisfied. This means, let's say AD is 10 to the power 5, while AC will be only equal to, let's say, 10. So what is AD upon AC? AD upon AC will be 10 to the power 5 upon 10, which is 10 to the power 4, which is a very high number. So we can simply say AD is greater than AC, and for all practical purposes we can neglect AC. So this term is neglected. So what the formula remains, V out equal to AD times V plus minus V minus, which is the formula for op-amp. So how does this formula come? This formula comes when AD upon AC is greater than 1. This concept mathematically, we can quantify this using a term called common mode rejection ratio. Now I'll write that term here. Yeah, so this was the expression. So we know that AD upon AC should be greater than 1. This is the condition that we have to fulfill. Now how do we check that? We check that by checking a number called CMRR. The formula for CMRR is 20 log AC upon AD. Common mode rejection ratio. This is 20 log AC upon AD. Now let's take an example, okay? Let's take an example. So let's say AD is again 10 to the power 5, and let's say AC is 10. So let's put these values here. Now this is a good op-amp because I told you AD is 10 to the power 5 is greater than 10. So let's put this value here. So we will get CMRR equal to 20 times logarithmic, this is base 10, remember. AC is 10 divided by 10 to the power 5. So we'll get 20 log to the base 10, 10 to the power minus 4. These gets cancelled. We get 20 times minus 4 minus 80 dB. I should clarify that these units here were dB, decibels. So what we get here? We get a gain of minus 80 dB. Minus signifies that the numerator is smaller than denominator, and the higher this number, the higher in the negative side this number is, the better your operational amplifier is. So again, just to summarize, CMRR denotes how good your amplifier is at neglecting this term, so that the formula simply becomes A equal to AD times V plus minus this open loop gain. This is A open loop. So in order to get a good operational amplifier, we must find ways to neglect this term, and we neglect this term by saying that AD upon AC should be greater. This is our requirement. This is our requirement. And how do we know whether we have fulfilled our requirement? We know that by measuring this number, this physical quantity known as common mode rejection ratio. This denotes, as the name suggests, how much of the common mode gain is being rejected as a ratio to differential gain. So the more negative the number is, the better our operational amplifier is, the more ideal our operational amplifier is, which is what we want. So a good amplifier would even have minus 100 dB. I'll take one more example. AD equal to 1000, AC equal to 1000. So AD upon AC, 1000 upon 1000, it's 1. This is a very bad. Why? This term and this term is the same. So you see what the formula becomes. I'll write the formula. So this will become 1000 times V plus minus V minus plus 1000 times V plus plus V minus divided by 2. So I'll take 1000 common. This will become V plus minus V minus, and this will become V plus by 2 plus V minus by 2. 1000 3v plus by 2 minus v minus by 2. This is not the formula for our open loop. Remember, our open loop formula for an operational amplifier looks something like this: v plus minus v minus. You can see the coefficients of v plus and v minus are same. They're not the same here. It's 3000 by 2 here, and it's 1 by 2 1000 by 2 here. So this is a very bad operational amplifier, very bad. That's right. And if we try to find out CMRR in this case, so we'll say 20 log 1000 by 1000. This will log 1 is 0, so it's come out to be 0 dB. Bad, very bad. So here in this case CMRR is equal to 0 dB. You can clearly see this is not even the formula for an operational amplifier gain. This is a very bad operational amplifier. This will not perform. This is far from ideal. That's why I say the performance here will be very poor, what we typically expect from an operational amplifier. Hence our aim, the person who designs the operational amplifier, they have to make sure that CMRR is high enough in the negative side, minus 80, minus 100, minus 90. That's an acceptable, that's not acceptable, that's a more than sufficient, good enough operational amplifier as far as CMRR is concerned. There are other terms we saw. Yeah.
But this for an ideal op-amp, the CMRR value must be infinite. So
yes.
the formula would be 20 times log of AD upon AC.
Okay, so when we say infinite, okay, let me just hold on a second. Let me just confirm the formula whether I'm can somebody confirm, is it AD by AC or AC by AD? As far as I can remember, can somebody confirm? Yeah, you're correct. It's AD by AC, sorry. So that's fine. Yeah, you're correct. It's AD by AC.
So you have told about the low pass filter. If the question will come about the high pass filter, then how will be the circuit?
Okay. So I'll just finish this. Okay, so CMRR is AD upon AC. You are correct. Let me insert a new slide. Yeah, so CMRR is 20 log AD upon AC. So we want this number to be very high, 80 dB, 100 dB and so on. Yeah, so you're talking about high pass filter, right? High pass filter? Yes?
Yes, sir.
Okay, so high pass filter circuit will look something like this. V in, this is ground, this is V out. This is your high pass filter circuit looks like. So let's derive the formula. Let's assume current I is flowing. I'll write KVL. So V in minus, remember that this can be written as ZC is 1 upon j omega C. So V in minus RC, IR. So I times 1 upon j omega C minus IR equal to 0. I get the value of I as V in upon R plus 1 upon j omega C. Now V out is nothing but, if I apply Ohm's law across this resistor, this will be I times R. So I value is V in upon R plus 1 upon j omega C into R. I do that. So this implies V out upon V in. This will come out to be, I'll simply take this downstairs. So this will come out to be R upon 1 plus j omega C. This will come out to be, I'll take j omega C up, so this will be j omega RC upon 1 plus j omega RC. This is the gain expression. So this is the gain expression, and as I told you, it will look something like this. So this is the cutoff frequency, which value would be, in this case again I told you the coefficient of j has to be unity. So I'll simply say omega C into RC equal to 1. So omega C we get 1 upon RC. So this is 1 upon RC, and the gain here we can calculate it. So this is the circuit, this is the gain, and this is the cutoff frequency, and that's how the gain will look like in dB. Yeah. Is it clear now?
Yes, sir.
Yeah. So yeah, thank you for correcting me. I always get I mix up these things, AD upon AC or AC upon AD. I just remember that, I do remember that AD upon AC should be greater than 1. That's it. And that's the thing I go ahead with. So usually things work out. There's sometimes a negative and positive sign. It's I get confused between them. But if you know the direction of current, and if you know what value should be higher, you'll get the correct answer. So don't worry. The concept is clear. Sign is how should I say this? It's a manifestation of the notation that we use, whatever which side we think is positive or negative. So yeah, and thank you for correcting me though. Okay. Yeah. So any other doubts do people have?
Sir, is there any question on logarithm or anti-logarithm op-amp?
Yes, there is no question, but there is no question, I think, but you can use operational amplifier to find the logarithmic and yeah, anti-logarithmic is I think exponential. Yeah, so you can do that, I think, if I remember correctly. Let me just try to find out. Let me just, because this logarithmic is also an arithmetic, how should I say, arithmetic operation, right? So since op-amp is being used to, we saw integrator, differentiator, and so on. Yeah, there is actually. So if we have to use logarithmic, then we have to use a device in which there is an exponential involved. So exponential, where do we find an exponential? Diodes. Yeah. So if we use diodes in our circuits, then we can try to find. Let me just try to Google this. Hold on a second. Let me try to find out. We should be able to. Yeah, I found it. Hold on. I'll share my screen. Good. It's a good point you raised. Are you able to see this on your screen? Hello.
Yes, sir.
So this is the expression that we have gotten. So this is the circuit that we have. Yeah. So you can see that it works. We can do that. So derivation would be more or less similar. Again, see, the things do not change. The KVL and the KCL and the virtual short concept, and that no current flows in here or out of here. So those things will not change. Those things will not change at all. The only thing is that the current expression will change here. So while writing, so again I'll assume the voltage is Vx here. So I'll simply write the current flowing here, Vi minus Vx upon R1 should be equal to. So now I'll write the expression for diode. So you must know the expression for diode is I equal to ID. What's that? E to the power. There is a
voltage by
VVD,
voltage equivalent of temperature.
Yeah. So no, I'm not just talking about temperature, just in terms of voltages. So there is a knee voltage when diode is involved. So if you are above that voltage and diode is conducting, otherwise diode is not conducting. So that's how an exponential term comes there, which will again, since there's an exponential involved in the differential equation, have they derived that? Yeah. So here they are doing that. So this is the expression for voltage. So IF is the saturation. We'll see this, but just assume this is the constant, and e to the power Vf is the applied voltage over eta Vt. Vt is a constant and eta is again a constant for a given diode. So just forget about these values. Just note that the current is exponentially dependent on the voltage applied. That's the thing. So we write this expression, and so this is the output that they have gotten. So output voltage is a logarithmic of input voltage. Simple. That's why it's called a logarithmic circuit. We saw integrator, we saw differentiator. This is a logarithmic. So very straightforward thing. And there must also be anti-logarithmic. Yeah, so exponential. So what we do, you remember that integrated differentiator. So R and C swapped their places here. We have swapped the places with diode with a resistor. Simple. Again, the concepts will not change. So if you apply KCL, KVL, and that's it, and Ohm's law, only three things, you will be able to solve any problem of op amp, any problem whatsoever. Okay, is it clear?
Yes, sir.
Okay. Thank you for asking this question. Yeah. Okay. So next week we'll be doing digital electronics. Simple. I'll start again. Very simple. What are logic gates, Boolean algebra, hexadecimal, binary, etc. And then we'll start slowly. We'll start building up. It's a very simple and scoring. Digital electronics is very simple and scoring. Just that when JK flip flops come and the sequential circuits, and they get lengthy, not difficult, just lengthy. That's it. We'll try to that's in the very, that's I think it will be 3 weeks later, but for the next 2 weeks we'll just do very simple questions, and if you have any doubts, feel free to send me. And yes, so thank you very much for attending. Any other doubts? Sorry, any other doubts you people have? Okay. Pratik?
Yes, sir.
Yeah,
Sir,
go ahead.
I have a doubt about constant current source. Sir, we generally used where we have to keep, so I don't quite understand the circuit of it, or
Okay.
how to make in practical things.
Okay, so we'll talk about that. We will talk about this actually. So constant current sources are usually made using BJTs, or that's bipolar junction transistor, BJTs, or MOSFETs, metal oxide semiconductor field effect transistor. So we use these devices, and we design a circuit using these devices so as to form a constant current source. We have a question about it. We will solve it, but I think that will come only in 11th session, because I have to build up to that. We need to first talk about diode, then BJT, and then circuits of BJT. So it is a question. We will discuss about it. So I require your patience and request your patience in regard to that. We will solve this tomorrow.
Okay, sure, sir.
Yeah. Thank you. Okay. Another thing? All right. If nothing, then um, let's meet next week, where we'll starting in digital electronics. Yeah. Okay. Thank you, everyone. Thank you for attending. Good night.
Thank you, sir.
Thank you, sir.
Bye bye.
Thank you, sir.